Hello, Mindsetters. I hope you're having a great time. It is a Saturday, and I'm not alone. My name is Abram. This is your favorite show, the best learning show ever, Learn Extra Live on a Saturday. Of course, we're doing your prelim questions. My name is Abram, as I've said. I'm joined by Mr. TK. How are you, sir?
I'm good, and you, Abram?
I'm Fukile.
Yes,
And
it's
Rasiput.
it's sort of with and Amunta, we're going to have some beautiful science learning. Nikonala, TK Ukona, just sit there and relax.
And the Mindsetters biko anala.
Definitely.
They're ready to learn more.
Well, welcome to your learning channel that is the best in the world, the best internationally. You sit there, you learn. Wherever you are, you get the best learning you can ever think of.
Exact. I wouldn't agree more. Can you just take us through what are we doing today?
Okay, well, today we're going to look at some chemistry revision. We're going to specifically look at some redox reaction section here, where we'll be looking at cells and you know what is involved there with redox reaction, transfer of electrons. We're talking about cells, we're talking about energy changes in there. Then we will look at something to do with organic chemistry. Okay?
All right.
And you know that with organic chemistry, your paper, basically, the second paper has got the largest part of it. It's organic chemistry.
I like that one.
Yeah.
You saw an but mindset is loco ulava ku join sanayena. There are three things that you need to know. One, you can download your notes on learnextra.co.za/live. They are all for free. And secondly, follow us on Twitter @learnextra. And lastly, my favorite one, be on Facebook, and let's just learn more on Facebook. Ask some questions and help one another, because I'll be posting some those questions that we're doing on our Facebook page. The link is facebook.com/learn extra. You should be knowing it by now. Otherwise, you saw an upward.
Ingo Moi Sungula ke hidon the physical sciences grade 12. Here revision young winner for the prelim exams. Let's have a look at the first question that we have for you today. This is a question that has been taken from the Eastern Cape preliminary exam paper 2, and it was the question 8 for that paper. All right, if you have that, because I know people from Eastern Cape are actually watching, if you have that paper, and even wherever you are, if you have access to that paper through the net and everything, have the paper and sit down with us and you learn. All right, so we're looking specifically at question number 8 now, and it says the following cell is set up in a laboratory, okay, by a group of learners. So learners set this cell up in the lab, all right? So there is the cell. You can see you've got silver there, you've got zinc, all right? And then you've got some silver solution there and some zinc solution there. And of course, there you've got a salt bridge. And this immediately should be telling you what type of an electrochemical cell we're talking about. And of course, we shall be coming back to it as we look at the questions that we have here. Let's look at the very first question. Wow. The very thing I was talking about is on your first question here. They say, what type of a cell is represented by this diagram here? If you look at it in that way, you've got a salt bridge, you've got half cells connected together by that salt bridge, and you don't have energy pumped into that cell, but you're seeing the cell actually giving out that energy. You must know that there you're talking about what we call the galvanic cell. Okay? So this is a galvanic cell. The next question, give the cell notation for this cell. Now, for this question here, if you are to give a cell notation, remember, you need to identify which of your electrodes is the anode and or the cathode, okay? So that you can tell which one to start with and which one to end up with. All right. Now, for us to do that, we need the table of standard electrode potentials, okay? And I have the table here with me. Let's just have a look at it. There is the table. You can see where it's zinc here. You can see there we have zinc, the zinc half cell there. Okay, that's what we have. All right, now from there, can we find the silver? We go down, we move down until we found where silver is. Look at where silver is, okay? There it's silver. All right, now, what does this mean? It means that because if you look at the table, although we didn't place the abilities on there, or the arrows that show us the levels of ability in terms of the standard potential abilities to reduce, you will know that from this side here, okay, as you go down, the ability to oxidize increases, okay? Now, this means we have oxidizing strength, okay? Increasing in that way. So that tells you that this silver here is more able to oxidize than what? Than zinc, all right? And because of that, it means that the substance that is going to be oxidized will be zinc instead of, as compared to silver, according to their strength, their ability to oxidize. Okay, now you would see here, let's come back here. You will see here that I have a summary of the table because we don't want to go through that whole table. There's a whole lot in here. There is zinc, okay? There is zinc, and now I'm including the E0 value there, the voltage there, and then there it's silver. But there's a whole lot more other substances in between before we get to silver. So this is just convenient for us to talk about them as we look at them. So we are saying silver will be more able to oxidize zinc. Okay, now what does that mean? It means that zinc will have this. We will have this for zinc. We will see zinc being oxidized. In other words, made to lose electrons. And it will be going into solution, and those electrons will be going to what? To silver. So this will be the oxidation half cell, if you like. So oxidation half cell. All right. And the silver, you've got Ag plus, will be reduced, and we will have silver. Okay, so let me be consistent here. That is solid. Sorry, I need to erase that. This is AQ, all right? This is silver in solution, silver ion in solution, Ag plus. And this will be the solid silver. Okay, and what will this be? This will be your reduction half cell. Okay, and once we are able to see this, we then can be able to write down the answer to this question here that says write down or give the cell notation. With the cell notation, you start with the oxidation half and you end up with the reduction half. And how do we do that? Remember, it is zinc that is being oxidized. So we start there. And then from zinc, it becomes zinc ions, 2 plus, in solution. You can do that as well to show the state in which the substances are. All right? And what comes here is what we call the salt bridge. And remember, you need that for the salt bridge. Double lines like that, and then you're showing salt bridge. And then on the reduction side, we're seeing the Ag plus ion in solution being reduced to silver atoms. Okay, so that then becomes what we call your cell notation. Okay, do not forget, you start with the oxidation, you end up with the reduction, and you must know the meaning of those double lines in between there to say you're talking salt bridge. Okay, now moving on. Which electrode, zinc or silver here, is the anode in this cell? Now, what is the anode? The anode is the electrode where oxidation occurs. Now, in this case here, like we have seen here, including the explanation that I gave earlier on, you would see that it is zinc that is being oxidized. And because zinc is oxidized, that zinc electrode will be the one that is the anode. Okay, so zinc, okay, is the anode. Even if you just wrote the symbol there, Zn, that will suffice. Okay, now moving on, we come to question number D here, still based on our cell there, the galvanic cell that we have. It says, what type of reaction takes place at the anode? Oxidation or reduction? This should be marks for free, really. They are just, these are giveaways. All right. Now, when we're talking anode, at the anode, we need to have oxidation happening. Okay? Oxidation happens at the anode. So you must collect those giveaway marks here that are actually given to you. So that's what we have here as the summary. Let me see, moving on with the same question coming to this point here. It says here, write down or write the half reaction. Write the half reaction that occurs at the anode. Okay? At the anode, I can't overemphasize this. You need to know at the anode, that's where oxidation happens. That tells you that at the cathode, that is where reduction takes place. Now, if I am to write down the half reaction that occurs at the anode, it means I must be talking about what happens to zinc, because it is zinc that is the anode. So I would have zinc, okay, becoming Zn2 plus the zinc ion, because it is now oxidized. It has been made to lose those 2 electrons there. So this is the half reaction that occurs at the anode. Okay. The next one talks about the half reaction that occurs at the cathode. All right? At the cathode, that is where reduction takes place. And therefore, we expect that at the cathode for this cell, this silver ions are going to receive electrons, and they are going to become silver atoms. Okay, so that's what is going to happen at the cathode. Now, the next question says that we need to use the answers we got to questions 8.15 and 8.16 to show the overall cell reaction. Showing the overall cell reaction, don't forget, you need to make sure that your half reactions, both oxidation and reduction, are balanced. And once that is balanced, then you can come to your net equation. And how do we balance that? You look at the number of electrons that are given off or that are lost through oxidation, and the number of electrons that should be received through reduction. And if there's a disparity between those two numbers of electrons, then you balance that. Once you do that, you will be able to get to the net equation. Let's just quickly do that. Okay, now if you go back here, you would see that zinc is giving away 2 electrons. But on the other hand, the silver ions, each silver ion can only take 1 electron, but 2 are given. So if we want to take all the electrons that have been given off by the zinc atoms, we would then say for every zinc atom losing 2 electrons, we will need 2 ions of silver to receive those 2 electrons, and therefore 2 atoms of silver will be formed. Okay, now that's just the explanation that I can give, but the quick way of looking at it, like I said, you just look at the number of atoms, electrons that have been given off, 2 electrons, and therefore you would make this one 2 here, then everything here would have to become 2. Now, what has happened now? Because in 8.1.7, we need to use this to find what we call the overall cell reaction. So what we need to do now that the number of electrons have been balanced out, we can then say, okay, taking out these electrons here because they are found in the first half reaction, the 2 electrons are on the right. And on the reduction half reaction, the 2 electrons are on the left. So they can be cancelled out. And then we can add the 2 half reactions together. Okay, now let's quickly add them. On the left, from the top side, I've got zinc. And then I don't have anything else. So I would say plus and then come to the second half reaction, which is my reduction half reaction, and check what do I have on the left after the electrons have been cancelled out. I see that I've got 2 Ag pluses. All right? Do I have anything else again on the left? No. That is the end of it. So I would say, okay, that gives us what is on the right-hand side. At the top, or the half reaction that shows me the oxidation part here, I've got the Zn2 pluses on the right, and that's all I have. So I'll write the Zn2 plus ion there, plus coming down here, on the right for my reduction half reaction, I've got 2Ag, and that has solved my problem. Okay, now we have done quite a few things here that are very crucial for you in preparation for your exams. We are coming back after a short break and we will continue.
Here's a quick question though,
Yes.
from Galvanic Paswana.
Yeah.
Galvanic says, is it important to show the phase? Will I forfeit marks for leaving the state of phase out?
Okay, good. Tagaran Paswana.
Yes.
That name rings a bell. Well, Tagalani, you're not going to forfeit any marks. So you choose, like I had earlier on, I would show the phases, all right? But then later on, I wasn't showing it. Okay, so it is not compulsory. You don't have to show the phases, but the chemistry has to be correct.
I
All
can
right.
support.
Sure. It's all.
All right, my sisters, just sit there, don't go anywhere. We'll see you after the break. Welcome back, Mindsetters. Now, if you're joining us now, you're a bit late, but you can still catch up. On the Facebook page, we have Mindsetters such as Gatlo Musikare saying, so far so good, they're enjoying the show, Mr. TK.
Wow.
But I have questions also.
All right.
The first one is from Tulufelo Rakomane. Tulu says, Mr. TK, am I right to assume that the substance that has the high oxidizing strength is the oxidizing agent?
Well, the one with a high oxidizing strength must be the reducing agent. So you got it wrong there. The one with a high oxidizing strength, I mean, must be the what's the question again? I need to get it. So it's a high oxidizing strength.
Yes.
Yeah.
Am I wrong to assume that the substance that has the high oxidizing strength is the oxidizing agent?
Yes, then that's correct. So high oxidizing strength is the one that is going to cause the other one to lose electrons. So it is the oxidizing agent. It's going to be the oxidizing agent. But then let me just have a look at this to continue to explain this to you. Now you would see that going down this table here on the right, we are having increasing oxidizing strength as you go down here. Now, even if we don't have this arrow here, we should be able to look at this pluses here. The one with the highest plus value will be the one that has the highest oxidizing ability. In the same way, the one with the highest value of the negative, with the highest, would I say, mathematical, or say this is the lowest negative value that you're having there. This one has got the highest ability to reduce. Okay, so it means that in this case here, lithium plus, lithium up there will be the one that's more able to reduce, okay, than any other that is below it. Okay, so that is how you can also look at this table and use it without the arrows on the left and right. But the arrows guide us to just say, look, as you move from top to bottom, there is increasing oxidizing strength. On the other hand, as you move from bottom up, there is an increasing reducing ability. All right, so that's it. Now let's have a look at the last part of the first question we started looking at, which is this question here. It says down here, calculate the EMF of the cell. All right, so we're still looking at the zinc silver cell, and we are to calculate the EMF of that cell there. The EMF, okay, the EMF of the cell, which is the E naught of the cell. All right, this we know is given by the E naught cathode minus E naught anode. Okay, so that's what we have. Now remember that I tried to reduce the table, okay, table 4b, so that we can only zoom to those that are involved in this particular question here. And then this is the table. Now let's have a look at it. Now, the anode must be the one where oxidation has happened. So this is our anode. Okay, so this is the anode. And the cathode must be the one where reduction is occurring. So this is our cathode. Okay, so the E naught says it's E cathode minus E anode. Okay, so let's just work on it now. There we go. So for the cathode, from here, we know that the cathode, we can tell that the cathode is positive 0.8. So we can therefore substitute here. There we go. Equal to 0.8. This minus there, and then for zinc, it's minus 0.76. You can confirm it in your table if you want to. Okay, so you can go back to your table and confirm it. Okay. Need to close that now. Okay, so minus 0.76, that's it for the anode, the zinc. All right, so once we have that, work it out. This is then okay, this is then 0.86 plus 0.76. And what do you get there? You can add the two, all right? So you've got 6, 8 plus 7 is 15, carry 1, so that is 1.56 volts. Okay, so that is the E cell. That is the cell EMF of the cell that we have here. Another thing that you should look up to when you're having this kind of questions here, it's that they can actually, although they didn't mention here, we're talking about standard conditions here, because those values that we have just used are actually based on standard values and standard conditions for that cell to be able to produce that particular EMF. And what are those conditions, although they are not mentioned here? One, you need to know that the concentrations of both the solutions must be 1 mole per cubic decimeter. And then you also need to take temperature into consideration, and that is at 25 degrees Celsius, okay? And then the other one, will it apply? The other one applies to gases. Will it apply to this specific cell here that we're talking about, okay, which is the pressure? No, because in this cell here, there are no gases. And because there are no gases, these other condition here that speaks to gases does not apply. And if there were gases, then we'll be saying that the pressure of 1 atmosphere applies there. All right, so we move on. Moving on, we're coming to this question here. It's question number 2. This was taken from the Gauteng Department of Education, paper 2, question 9. And then the diagram here, immediately there's something you should be spotting a difference between the diagram of a cell that we worked on earlier on and this one that we're coming into here. All right. The diagram below shows an electrolytic cell. So we also have an electrolytic cell here, which is used in the purification of copper. All right. Now, when we're talking purification, we're talking electrolytic cells. We're talking about electrochemical cells that are electrolytic in nature. We can't be talking about galvanic cell. All right. Now, write down 2 differences between an electrolytic cell and a galvanic cell. Right. So let me just do these here. Say here we've got an electrolytic cell. Electrolytic cell, and then we've got galvanic this side. Okay, so we can have some sort of table here, and we're going to use it to write down the differences between the 2 types of cells. In an electrolytic cell, the quick one that should always be in your mind, I mean, you shouldn't forget this one, is that energy. I do have this here. Maybe let's just, let me just explain it to you because I have the table here. I should have just gone straight to the table. Okay, so let's just come to this table here that gives us the difference between the 2 cells here. All right. Now, with an electrolytic cell, what do we have? The first one, like I was saying, it's your energy changes. We see here that electrical energy is converted to chemical energy when we're talking electrolytic cell. But when we're talking galvanic, we've got chemical energy converted to electrical energy. So that's what we have. Okay. Another thing that you need to know is that the reaction that occurs in an electrolytic cell is non-spontaneous. So you have to force it to happen. That's why you have to supply energy in the form of electrical energy to get the reaction to take place. So the reaction is non-spontaneous this side, whilst it is spontaneous that side. Okay, spontaneous there. The anode is the positive electrode when we're talking electrolytic cells. And you're going to see when we unpack that question there further. All right, whilst with the galvanic cell, the anode is the negative electrode. The other things that you have noticed is that with an electrolytic cell, you've got one particular solution, and both electrodes are dipped into that same solution. But with a galvanic cell, you've got 2 distinct solutions in which the 2 electrodes are, placed, separated like that. And then you would also see that you've got the salt bridge, okay? You've got the salt bridge on the galvanic cell, but you don't have a salt bridge on the electrolytic cell. So this is, in summary, the differences that you need to look at. But then they were only asking for 2. Just put any 2 of those and you get your marks. We're moving on. It says write down the following, okay, or write down the letter A to D that represents the following. Impure copper, all right? Remember here we are purifying copper. So which letter will be showing impure copper? Impure copper will be things that are getting deposited down at the bottom here and on the side of the electrode or the positive electrode, let me put it that way, okay? Because that's where the oxidation will be happening. All right, so B will be showing that. Coming to Roman figure 2, impurities formed during electrolysis. Okay, now the impure copper, it's this, is the electrode, this one here. So the answer for first one will be A, and the impurities will be the things that I showed at the bottom here. That question there, so I thought it was talking about impurities. The impure copper is A, all right? And the impurities is B, the things that are just below the impure copper electrode there. All right, and down here, the electrode onto which pure copper precipitates. You will have pure copper precipitating this side here, because this is where the reduction is happening. So the copper ion, okay, receives electrons there. The copper ions receive electrons there to become pure copper on this electrode here. Okay, and therefore whatever precipitates down here, it's pure copper. All right, so the electrode where pure copper is precipitating is D. All right, so that is D. Okay, so the answer here will be D. C, in which direction will the electrons in the external circuit flow? Only write A to D or D to A. Now, if you look at the cell, where are the electrons being used? The electrons are used this side, like I have written that particular half reaction there, or half cell reaction there. Now, if the electrons are to be received here and be used to take up this copper ions from the solution, surely these electrons should be moving from A to D. Okay, so this is the path of the electrons. So electrons should be moving from A to D. All right, so the answer is this one here, and you get your 1 mark. Okay, now moving on. Write down the half cell reaction that occurs at the anode. Now, the anode, it's this part here. Here you've got impure copper, okay, that oxidizes to copper and gets into the solution. So more and more of these things from the impure copper are moving into the solution. And on this side, you can see that they are now taken out to give you pure copper. Okay, so that is the side where your anode is, and that's where the oxidation is happening. Okay, so I think at this point, we would need to pause and have some break, and to you, Abram.
I think we'll also take some questions after that break.
Okay, sure.
Having said that, thank you to the mindsetters that are on the page, Renzi and also Takalani Paswana, who's making a huge impact on the page, answering the questions and helping other mindsetters. That's the spirit that we want. Let's keep on helping others on facebook.com/LearnExtra. See you after the break. Welcome back, Mindsetters. Now, also a huge, a big highlight, shout out to one of my friends, also our loyal Facebook fan, Sovo, who just joined us on the page. Welcome, Sovo. But Mr. TK, I have another question for you from the Mindsetter.
Okay.
Ready for it?
Yebo, let's
it's
hear
from
it.
Tabang Matanta.
Yeah.
I thought it's Matata, so he's
Okay.
bringing us Matata. But no, it's Tabang Matanta, saying, do electrons move from anode to cathode through salt bridge or through the external circuit in the galvanic cell?
Oh, yeah, good question, Tabang.
Yes.
Good. Now, let's go back to this page here, so I can use this diagram here to explain it, Tabang. Yeah, if we have a galvanic cell like that, when we have a galvanic cell like that, where is my colors? Yeah, good. Now I've got it. Okay, in a galvanic cell like this, Tabang, what we're going to have is that this from here, these wires that have connected here, we call that external circuit. We call that the external circuit. And it's through this external circuit that electrons move. Okay? So electrons move in wires. Electrons cannot move in solution. All right? So for electrons to move, they are to use the external circuit. So they move from the anode, which is this part here in this case. So electrons move from there. Right. Electrons move in that direction. Okay? From anode to cathode in that way. Inside the cells here, okay, inside here, only ions move. Only ions move. And what do we mean by ions? These are charged atoms, these are charged combinations of atoms that can only move within that solution, within solution. And remember that your salt bridge is made up of a saturated solution. Saturated ionic solution. Okay? So that saturated ionic solution, it's responsible for allowing ions to move from one side to the other. Remember, it has to, and if you look at the salt bridge being a saturated solution, it means that the ions from the half cells here cannot necessarily go in there, but they have to come out from the salt bridge. So ions from here, say it's KNO3. Let me just use that example. The pluses are the Ks and the minuses are the NO3s. Okay? Now this side with oxidation, you're having a lot of the pluses coming in the form of Zn2+. So for you to keep neutrality, because that is the function of the salt bridge, for you to keep neutrality in the two solutions, you will need to take the positives from the salt bridge. So these pluses, the K pluses, you will need to take the minuses in this case. Sorry about that. So let me erase this part here. Okay. You will need to take the minuses instead. Okay? So you will need to take the minuses instead, because you're pumping in a lot of pluses into this side. So the minuses come in there. The NO3s that are minuses come in there to stabilize, to keep the electrical neutrality. On the other hand, this side, the Ag plus is being taken from the solution. So Ag plus gets out of the solution. Right. So Ag plus Ag pluses. So Ag plus this side are taken out of the solution to form your silver there. So this one is depleted of the pluses. So the K pluses come in here to maintain that electrical neutrality. So that you must understand, each one of you, no electrons are moving inside the solutions. Electrons are only moving in the external circuit. Inside the solutions and through the salt bridge, it's only ions that are moving. Okay, good. Now let's move on. Okay, so we are at this point here. Right, we are at this point here. Write down the half cell reaction that occurs at the anode. Okay, so the anode, that's where oxidation is happening. So it is the impure copper where we have got the copper solid becoming copper 2+, okay, and the 2 electrons. Okay, so that is copper 2+. Okay, so copper 2+. Okay, so that is what is happening here at the anode. And the anode is, of course, positive for this particular cell here. And the next Give a reason why the impurities formed as a byproduct have economic value. Okay, now if you look at this, what are we doing? We have mined copper and we have compacted it into an electrode, and then we immerse it in that electrochemical cell there, electrolytic cell. And then we connect it to the positive terminal of our energy source so that oxidation will happen on it. Okay. Now, as that oxidation is happening, you've got impurities down here, you've got impurities down here. These impurities still contain some amount of copper ions or copper, some amount of copper and also and other metals, other expensive metals, let me put it that way. And because of that, because remember, this is something that has been mined. You can't just think it is all copper. Majority of it is copper, of course, but there are other metals that are there that are useful, that can be very expensive. There could be some bit of platinum in that, and we know that platinum is quite expensive, very valuable. Okay, so because of that, these byproduct, we don't just throw it away because it has got an economic value. All right? Okay, so these byproduct, so the byproduct contains various expensive metals or metals. Economically, so that can be sold and of course be useful economically. That's why it is so useful. Okay, so moving on.
Before you move on,
yep.
Sitya says, so are you saying basically ions move the opposite terminals as to those of electrons?
What is happening here, remember that electrons move from the anode to the cathode. Now, the ions, I really want to stress this. The ions, because you've got a saturated solution of your salt bridge, it means that your ions are moving at first. Your ions are moving, it's ions in the salt bridge that actually move in opposing direction. The minus ions will move, in this case, towards the zinc solution because you are getting more of the zinc 2 pluses. Remember, the duty of the salt bridge is to neutralize, keep electrical neutrality of the two solutions. So you have that. And this is from the salt bridge only so far. Pluses would come this side because you are depleting this side of the pluses, which is the Ag plus, the Ag plus going into this electrode, clinging onto it as Ag. Okay, I think I wrote Ng there. All right, clinging onto it as Ag. Okay, and because of that, you are depleting the pluses on this side. So the pluses on the salt bridge come that way. But of course, with time, when this saturated solution is actually now messed up, it has been, most of the ions have been removed. We can see the pluses moving from this side, but that will take a long time. The pluses moving from that side to the left, and we can see the minuses moving from the side to the right. Okay, but that would only happen much later in that particular situation. But firstly, what happens, that's why you have to make your salt bridge saturated. What happens is exactly what I have explained. I hope this, but for you, just understand this. Electrons move in the external circuit. Ions move in the solutions through the salt bridge. Finish and clear. That's what you need to know. Most of what I've explained now goes higher up into first year, second year, third year chemistry level. So don't really, but use that to understand what I'm trying to show you here. Now let's move on. We're coming to this question here. This question 3 was from the Eastern Cape paper, and it was the question 9 in that paper. It says the common lead acid battery used to start motor vehicles is composed of a number of galvanic cells, each having an EMF of about 2 volts. These are connected in series so that you can have voltages adding up to each other. Most motor vehicle batteries contain 6 of this type of cells we're talking about, and they give out a potential difference of 12 volts. But 6 volts, 24 volts, and 32 volt batteries are also available. Okay, now let's come down here to the questions. It says, the first question is the lead acid battery an example of a primary or a secondary cell? Explain your answer. Now the lead acid battery there, it's a secondary battery. Why? Why is it a secondary battery? It is because it can be recharged. You can charge it. Okay, it can be recharged. So you use it, it's finished, you recharge it, you can use it again. In the vehicles, in motor cars, there is the alternator that constantly charge the battery so you don't run out of the battery to start your car. All right. What type of energy, or before I move on, now we're speaking of secondary battery here, or secondary cell. That would be a secondary cell. Primary cell is a cell that cannot be recharged. This one can be recharged. Simple as that. That's how you will define it. Okay. What type of energy transformation takes place in the cell whilst it is discharging? Okay. So it is discharging. The cell is discharging. What is happening? In other words, when the cell is at work. All right. These are galvanic cells, so we know that the energy conversion is that of chemical energy converted into electrical energy, transferred into electrical energy. Okay. Right. Transferred into electrical energy. Because we know we're talking galvanic cell here. Galvanic cell converts chemical energy into electrical energy. Okay. Then down here we are told 98% of a lead acid battery can be recycled. Name 2 components of the battery that can be recycled and explain in your own words how they are recycled. Okay, now in a battery, or battery like this, a locomotive battery, the accumulator, as we would call it sometimes, there are 3 components that we should know. 1, we have the casing. Okay, this is that usual black or red plastic of your vehicle battery. Okay, that we call it the casing, and then inside it, it's divided into cells depending on the kind of battery we're talking about. If it's a car battery, it will have 6 of those so that it can add up to 12 volts. Okay, so that's the casing. And 2, it also have those terminals where you connect your battery into your car so that it can supply energy to your car. And those points are made of lead, okay? So these are lead grids, if you like, okay? And then you can call them lead terminals. People also call them that, okay? But these are the electrodes where you connect your plus minus to your vehicle. And thirdly, we also know that these acid batteries contain acid, and hence the name is acid battery. Okay, so those are the three components. And out of the three, the two can be recycled. But the acid cannot be recycled. Okay? Then if we are to safely dispose the battery into the environment, the acid, what do we need to do? We will therefore need to neutralize the acid for safe disposal. Okay? Neutralize the acid. Remember that when you add a base to the acid, you have neutralized it. You have actually made it to become water. Then it is safe to dispose it without harming the environment. Now, the ones that are recyclable are those two there. Now, how do we recycle them? Because that's what the question wants us to do. One, the casings can be broken into small pieces. So you break it into small pieces because it's made of plastic. After breaking it into small pieces, you can then melt it. Okay, after melting it, you can then remold it. Into new battery casings. Okay, and that is one of the reasons why when you are to buy a new car battery, they want you to bring back the old one. So that one serves as some deposit to your new battery. If the new battery was 1,000 Rand, maybe that one would give you plus minus 200 Rand or 300 Rand, so you pay 700 or 800 Rand for your new one. Okay, so why? Because they are aware that they can recycle this. The second part that can be recycled is of course the grids, the lead grids. Okay, the same thing. You clean them. Okay, you clean them, and even with this part here, the plastic, you break them down, or and clean them afterwards, or you can clean them before. So even cleaning here is involved. So let me put cleaning here. Cleaning is also involved there. Okay, so this side you clean them as well. You clean the grids. You can then melt them as well and remold into new battery grids or terminals. Okay, so this is what you do when you recycle these things here. We recycle things because, one, we don't want to harm the environment. Okay, we don't just throw them the way they are into the environment because we're harming it. And harming the environment, we are harming ourselves. Okay, so we recycle them. Now, if this question was saying, mention or write down 3 things that can be done to ensure that when you dispose these type of batteries into the environment, you don't harm the environment. You will include all these things, including the acid part that I spoke about. But if they just talk to you about things that can be recycled, the 2 things can be recycled: the plastic casings and the grids or the lead terminals. Those can be recycled. The acid, you can't recycle the acid. The only thing you can do to the acid to ensure that when you dispose it off into the environment, it is safe to do so, you neutralize it. Okay, so I will hand it to Abram now. I think we might need some fresh air
Indeed.
before we continue.
But two things that I need to say before that ad break. One is that we always tell the mindsetters to tweet us at LearnExtra. Here's a tweet that I have for you. It's from Katla Prince. Katla says, wow, Mr. TK, the best teacher ever. I'm going for physical science distinction this year.
Wow.
Awesome
wow.
tweet.
Thank you for that.
We've retweeted. Thank you very much, Katla. And the second thing that I need to tell you is that mindsetters help us. We need your help because Mindset is looking to hire someone. If you know of anyone who will be interested in doing a grade 10 to grade 12 CAPS aligned content development, review, and video presentation, tell them to visit mindset.co.za/learn/jobs. Otherwise, the closing date is the 26th of August this month. So hurry up and let's help one another. For now, we'll see you after the break. Don't move. Welcome back, Mindsetters. I hope you've just chilled down a bit, but you are ready to learn more with this because that's how we do it on LearnExtra. Have your phone next to you or your computer next to you because we learn more socially because we're young, we're fresh, vibrant, and intelligent. This is Physical Science with me, AB, and Mr. Dinyuko.
Yes. Now, any more questions? But then I think we can just continue with, and now we're starting with something else different. If you have questions, and I think Abram now has been a very good learner in physical sciences. He can answer some of the questions that you're having there. Now, coming to question number 4 here today, we are actually now switching on to organic chemistry. Now, let's just have a look here. This one was from the GDE Prelim paper, and it was 3.1. There are 2 structural isomers within the molecular formula C2H4O2. Define the term isomer. Okay. Now, how do we define that the term there? All right. Isomer or isomers. Isomers are organic molecules. So we're talking organic molecules here with the same molecular formula. Okay, but different structural formulas. Okay, but different structural formulae. Okay, so you have, when you are to write down the molecular formula of that substance, or maybe there could be 2 of them together, you come up to the same thing. This is an example of a molecular formula. But when you write down structural formulae, you can have 2 substances that are far different chemically. They are not the same, and they behave different chemically as well. So they behave differently chemically as well. So here we are. You write down the structural formula of these 2 isomers. Next to each isomer, write the IUPAC name. Now, what I'm going to do here is to write down that formula first. So the molecular formula is C2H4O2. Now, when I have something like this, with the oxygen, with the hydrogens, and the carbons, if I'm talking isomers, there are 2 things that come to mind already. There could be an alcohol and an aldehyde. And let's just have a look if that is not the case here. Look, if I've got the first one here, I can have the 2 carbons. I can have the hydrogens like that. Okay? And I can have, so you see, I've got, let me see what's happening here. Or I can also have an acid. So let me just erase what's happening here. Let me just erase what I have here. I must have 4 hydrogens. Okay? So with 4 hydrogens, I can have this one, yes. I can have this. Then, because I must have 4, I would have a double bond to oxygen there. You can see that I've got one oxygen gone already, but I have a second one to put. So that second one would be, could be something like that. And already I've got an acid here. So earlier on what I said, thinking about, we can think of an alcohol, you can think of an aldehyde, you can think of a carboxylic acid, okay? You can also think of an ester as well, okay? All these ones will contain hydrogens and oxygens together with carbon. Now, the second one, let me use this space here, okay? The second one, again, having 2 carbons like that, and I must have 2 oxygens, and I must have 4 hydrogens. But it must not be an acid again. And what is this acid here? I've got how many carbon atoms here? I've got 2. So the IUPAC name of this acid is what? This is ethanoic acid. So this is the IUPAC name of this molecule here. Now let's try and come up with the second one. All right. Now, if I have the carbon like that, all right, and I have my hydrogens there, and I only have one more hydrogen to show, one way of doing this would be to, let me put here. Why is this thing here? All right, that's fine, doesn't matter. Okay, so I've got that one here. If this can be an ester, how is it going to be like? If it has to be an ester, I need to have an oxygen, again, double bond oxygen to carbon like that. So I'll have a carbonyl group, okay? And where will the other oxygen be? All right. So for me to have the other oxygen, and I'm talking an ester, this bond here between the carbon and the carbon would have to be broken down, and I have, so let me just put it this way. So I would have the oxygen here, the carbon there, double bond to oxygen there, and I'll have a hydrogen there. And what do I have? Look at what I'm now having. I'm having structures that are not the same, but the molecular formula is the same. So the two substances here, this one and this one, are what we call isomers, because they've got different structural formulas, but the same molecular formula. And what ester is this one, if you look at it, okay? This, remember with the ester you start with your alkyl radical. This is a methyl group. And when you look at this part here, okay, so let me come to this part here. Let me even do that so that you see it. This has got nothing, this hydrogen has got nothing to do with this part here. So this one here, again, is what? One carbon, but with the O oxygens in that, in those positions there, then you know it will be a methanoate. So this is methyl methanoate, the ester. Okay? So I have the acid and the ester in this particular situation here. All right, not the alcohol, not the aldehyde. All right, so moving on, let's see what we have here. Question number 5, adapted from, again, the Gauteng Department of Education, paper 2, question 3.2. The letters A to D in the table below represent 4 organic compounds. Okay, so we've got the 4 organic compounds there, A, B, C, and D. Now, A, it's C4H6, Not very clear, so let me write it down for you. C4H6. 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 So that's what you are having there. And then you have this structural formula on B, and you have got another structural formula on C, and then in D, what you have is butane 2-on. Butane 2-on. Now, this is obviously a ketone. All right. So that's what you're having there. Now, let's move on to answer these questions here. Write down the letter representing a compound with a methyl branch. Okay? So a methyl branch, right? Which one will contain that? Methyl, it must have one carbon atom on it with the 3 H's. That's a methyl. Okay? Now, this one is the one that has a methyl branch, because look at it. You can look at that as the longest chain, and it's that of propane, and this one is a branch with a 1 carbon atom there. Therefore, it's a methyl branch. So the one with that is C. Okay. The next one, the letter representing an unsaturated hydrocarbon. Now, unsaturated hydrocarbons, remember, here we're talking about hydrocarbons with those that have got double bond between carbon atoms. Okay. Double bond between carbon atoms. Okay. Like that. And then you can still have others coming. Or you can have the alkynes with triple bonds between them. So you look for something like that to answer this question. Okay. And going back to that table there, which one is it's unsaturated? Letter representing a hydrocarbon that is unsaturated. All right. If you look at the first one with C4 and then you've got H6. If you go back to this formula here for alkanes that are saturated, you will see that with C4 you would have 2 into how many carbons? 4 plus 2. You should be having 2 times 4, which is 10 plus 2, 12 hydrogen carbons. But what do you have? You only have 6 there. Okay, so if you have 6 there, there is something else. Because if you had 12 and you come down to 6, okay, it means that some of these things, or these spaces has been taken by something else. It could well be that here you've got a cyclic molecule. But I don't want to get there yet, all right? And if you come here, this is saturated, that is saturated. Butane 2-on, all right? It is also saturated. So here, what an unsaturated hydrocarbon, the one with only hydrogens and carbons, you can see that your one, it that would only be A there, because you had to compare A and C. These two are hydrocarbons. These are not exactly hydrocarbons. They also contain other substances that are not necessarily or other atoms that are not necessarily hydrogen and carbon. Okay. The homologous series to which B belongs. Now, if you look at B, what are you having with B there? You've got one with an oxygen caught in between carbon atoms, which is this part here, Okay, that oxygen caught in between atoms, and you've got a double bond to oxygen there, and an H there. That tells you we're talking an ester. All right. Then moving on. So here, the homologous series to which B belongs is esters. Right. The IUPAC name of C, you come to C, let's have a look at C. Now look at C. C, it has got long chain 3 carbon atoms. And the carbon atom to which the methyl group, so this is your methyl group, is attached, is the one in the middle. So it doesn't matter from which side you're going to number your carbons. So let me just number them from left to right. Okay? So I've got that. So the main name, it's propane, okay, because I've got that. But I've got the methyl group. Where is the methyl group? All right? It's on carbon number 2. So there, I will call this one 2-methyl propane. 2-methyl propane. So that will be the name there. Okay? Now moving on, coming to the structural formula of D. Okay, now let's go back to D. Now if you look at D here, D is a ketone, all right? And it's butane 2-on. Okay, so butane 2-on. Let me write that name down here for you. So it's butane 2, not 2-1, but 2-on. It's not like a score in a soccer match, so it's 2-1. No, it's butane 2-on, because actually this thing is butanone. Okay, these two here just tell us where is this on placed. Where is this carbonyl group where the double bond to oxygen is. So what I'm going to have here is, I'll have, because we're talking but, I'll have 4 there, all right? And then but 2-on, so if I number my carbon atoms from left to right, if I call this one 1, this one 2, that one 3, that one 4. In these 2 here, that is when I will have the carbonyl group, okay? And then I will have the hydrogens there. And because of that, because of this carbonyl group there, I've got a ketone, and this ketone is butane 2-on. All right, that's where the carbonyl group is. That's the functional group of ketones. All right, nice. Moving on, we will be coming to question number 6. Okay, so there is question number 6. Now, question number 6, a very special question that is going to teach you quite a lot of things, and some of the things, I think that's where one area where most people are battling in organic chemistry. So please watch that as we come back to question number 6. We'll have a short break.
This is the end.
Is that the end?
You still want to learn more?
Wow, I thought we still have more time. Okay, now, well, we will have to say, therefore, that you go and do that question when you have your own time.
Exactly.
And good luck.
The question is on our Facebook page. We have the link also to the notes, so you don't have any excuse. But otherwise, thank you to all the mindsetters that have been on our page and helping other mindsetters, such as Nsovo, all the way from Malamulele in Limpopo. So thank you very much. She's always also on the page. So thank you very much.
We'll keep it up.
As well to other mindsetters that are always keeping me entertained on the page, such as Karabo and Kabelo and other mindsetters. Thank you so much for today. That's where we end it on Physical Sciences. We say peace.